Okay, so now that we've talked about cell potential or standard cell potential, I want to relate these back to two thermodynamic properties we talked about earlier, which is free energy and equilibrium, because it turns out that there is relationship between the three. So all of these are measures of reaction spontaneity. I think previously we talked about how standard free energy is a measure of reaction spontaneity, and we're going to see more how equilibrium constant K is as well. So if a redox reaction is spontaneous, all three of these must be true. The standard cell potential must be positive. The standard free energy is negative, we already knew. And the equilibrium constant K will be much greater than 1. It'll be greater than 1. So now I'm going to talk about how equations that relate each of these variables, right? So we're going to look at two variables at a time, and then we're going to look at how we relate all three of them. So let's start with the relationship between standard cell potential and the change in standard free energy. So here's our equation that relates the two. Our standard change in standard free energy is equal to negative N times F times the standard cell potential. So N is the number of moles of electrons that are transferred in the balanced redox reaction. After you balance the redox reaction, N will give you the number of moles of electrons that are transferred. F is called Faraday's constant. This is the charge of a mole of electrons, which is equal to this value here. And forgive me, this should be times 10 to the fourth. And I'm going to change that right here. Okay, times 10 to the fourth. Joules per moles times volts. We already know, right? So again, this not its standard conditions. Delta G is our change in standard free energy. E sub cell is the standard cell potential. So notice that standard cell potential and the change in our standard free energy have opposite signs. They have opposite signs, right? Because when a reaction is spontaneous, this E sub cell not value will be positive and delta G not will be negative. Okay, so just like all reactions that we've looked at, redox reactions also will reach some state of equilibrium. And so to relate equilibrium, our equilibrium constant K and our standard cell potential, here is the equation. E sub cell equals RT over NF times the natural log of our equilibrium constant K. Now, under standard conditions, right, where the temperature is 298 Kelvin, we can solve RT over F. So we put in our gas constant, 298 kelvins for our temperature, and Faraday's constant here, and we get 0.0257 volts. So if we substitute in that value for RT over F, this equation will reduce to standard cell potential equals 0.0257 volts over N times natural log of K. So this equation is only true when we are talking about standard temperature, right, at 25 degrees Celsius. At another temperature, we would have to use this equation here and plug in whatever that temperature value is. So, looking at this equation, if the standard cell potential is positive, K must be greater than 1. And you can literally play around with this, right? Plug in some numbers. K will be greater than 1. And if our standard cell potential is negative, K will be less than 1. So for a spontaneous redox reaction, K must be greater than 1. All right. So putting it all together, here are our equations that relate, right? This equation relates delta G and E sub cell. This relates standard cell potential and equilibrium constant K. And this is the equation that relates delta G and our equilibrium constant K. So let's summarize these three properties. So if K is greater than 1, delta G is less than 0, and standard cell potential is greater than 0, the reaction is spontaneous under standard conditions. And the products will be more abundant at equilibrium. The products will be more abundant at equilibrium. If K is less than 1 and delta G is greater than 0 and standard cell potential is less than 0, the reaction is non-spontaneous under standard conditions, and the reactants are more abundant at equilibrium. If all three of these are equal to, not all three, I'm sorry, if K is equal to 1 and delta G and standard cell potential are 0, the reaction is at equilibrium under standard conditions. And the reactants and products are equally abundant. So go back to the expression for how we generate our equilibrium constant K so that you can mathematically see why the products are more abundant here, the reactants are more abundant here, and then they're equal here.